all the packages are already imported in this case, and the data is also loaded. So the data is in two files. One is class 1 train and the second is class 2 train. And class 1 train contains two columns and class 2 train also contains two columns. Here I have printed 10 rows from class 1 train. So first column contains the first dimension of your feature, that is x1, and the second column contains the second dimension of your feature, that is x2. And similarly, we have two columns for class 2 train as well. So the first thing that you have to do is you have to visualize the training data and you have to generate 2D scatter plot of the training data. So when you do this scatter plot, what you have to do is you have to plot x1 along the x-axis and x2 along the y-axis. And you have to do it separately for class 1 train and class 2 train on the same figure. And when you do the scatter plot, you have to visualize class 1 in red color and class 2 in blue color. So, do you have any questions on this part?
Two separate scatter plots will come, right, for class 1 and class 2.
Sorry, I did not get you. Could you tell it once again?
So we have to draw a scatter plot for class 1 and class 2, right? There are two separate scatter plots, right?
Yeah. So you can. So you have to use the same figure, but you have to call the. So this you have to use scatter, and you
Yeah.
have to call it twice for the two classes, but you have to do it on the same figure so that you can see where the points lie in the two classes.
Okay.
Uh, does it clarify your question?
Yes, thank you.
Cool. Okay, then I'll move ahead. So now comes the interesting part, which is maximum likelihood estimate of parameters. So there was a typo in this question, this small typo. So if you look at your notebooks, there was a slash line over here. That should not be there. So this is the correct format now. So we will model the likelihood. So as you know, the likelihood is probability of the feature given the class. So this is likelihood for first class and this is the likelihood for the second class. And we will model them as Gaussian distributions. So for the first class, we have mu1 and sigma 1, and for second class, we have mu2 and sigma 2. And for each of class 1 and class 2, we can compute these three parameters pi, mu, and sigma. So this pi is will give us our prior, and mu and sigma will help us determine the likelihood, because once we know mu and sigma, we know what the Gaussian distribution is. So you have to estimate these three parameters using the formulas given on the right hand side. So yeah, so the first thing is, if you notice here, we are using this indicator function, which says whenever the target of ith data point is k. So k for us will be just class 1 and class 2, or you can call them like 0 and 1, because yeah, because when you load the data, this will be first column 0 and this will be second column, which is 1. So in this case, since the data is already separated into two parts, so it will be much easier for you to implement these functions directly, because you don't really have to use this indicator function. So essentially what you have to do is, for pi k, the numerator term is will give you the number of points in class 1, and the denominator is the total number of points, that is points in class 1 plus points in class 2. And so how do you find out the number of points in class 1? You can just find out how many rows are there in class 1 train. That will give you the number of points in class 1. So finding out pi k is quite straightforward. And when you come to mu k, this is essentially the mean of all the features in each class separately. So what I mean is, when you have your class 1 train, if you take mean of all of these, that will give you the mu k. And when you have class 2 train, and you take mean of all of the values, that will give you mu 2. Now, one important thing to note is, when you take the mean, you don't want to take the mean over all of these values. as you want to take the mean along the columns, because finally your mean will be a two-dimensional vector. So basically when you take the mean, say class 1 train dot mean, and then you have to pass this value x is equal to 0, so that you take the mean along the column. It should have been here. Okay. So far, do you have any question how to compute pi and mu? Okay, then I will go ahead. So the next thing to compute is the variance or the covariance or the sigma. So essentially, you have to compute the covariance of all points in class 1 and class 2 separately to compute this sigma value. So out here, there is one thing that will be helpful in your computation. Uh, I just want to make sure, can everyone hear me clearly? Oh, okay, that's perfect. Okay, so yeah, so computing mean was pretty straightforward because you could just do mean along the column. But computing sigma is slightly complicated. So I'll teach you a NumPy trick that you can use for this value. So let's look at that trick. Okay, so this is a matrix multiplication trick in NumPy. So you already know how to multiply 2D arrays. It's like normal multiplication in mathematics. So if you have P cross Q and Q cross R, your output will be P cross R. But if you have 3D arrays, how do you compute matrix multiplication? Let's say you have A, which is of shape n, comma p, comma q. So you can essentially think of it as n matrices, n separate matrices, and each of them have a shape of p, comma q. And if you have, say, B, a 3D matrix or 3D array of shape n, comma q, comma r, you can think of it as n separate matrices, each of which has a shape of q, comma r. And they are basically stacked together. So if you have q, comma r and stacked together, so you get n, comma q, comma r, and n, comma p, comma r. Now if you call np.matmul on a, comma b, the result will be of shape n, comma p, comma r. So essentially what it will do is it will take each of these p, comma q and q, comma r and perform a matrix multiplication of p, comma q cross q, comma r, and it will do it separately for each of your matrices along the n dimensions. So if you have to perform n matrix multiplications, you can do it all together in just using one command, using this trick. So do you have any questions with this? All right. So if you don't have any question, then I will take an example and show you. So if you have A of shape 2 comma 3 comma 1 and B of shape 2 comma 1 comma 3, so this first dimension should be same for both the arrays, and they should be of the form P comma Q and Q comma R. So this second one and this first one should be also the same, and then you perform math. So your output shape becomes 2 comma 3 comma 3. Now we can use this trick to compute the covariance matrix from our data. So remember, when we are doing covariance matrix from our data, essentially what we are doing is we are doing x minus mu multiplied by uh, x minus mu transpose, and then we are doing it for all data points, and then we are taking average over all of those data points. So one option is we can run a for loop and do it for all of the data points, but the smarter thing to do would be to use this matrix multiplication trick. Now it's it's good to use this matrix multiplication trick because this computation runs faster than if you write a for loop, because if you do anything inside NumPy internally, it does it in C++ and that's faster. Okay, so let's say your data is of is I'm just okay. I see some questions. So Amit sir, could you help me take the questions?
May I
Sorry.
ask my question?
Yeah, go ahead, please.
Yeah.
I
Yeah, so
I forgot to unmute myself. Go ahead.
instead of using this matrix multiplication, I used an np dot sum over the normal dot product of the two matrices.
You
That
took a
slow
NP
or is
dots
that?
and then you divide it by the total number of elements.
Yes, yes.
Yeah, I think that should also work.
And what if I mean, oh yes, yes. Thank you. That's it.
Yeah, hi Ankur. I also have a question. Uh,
Go ahead.
Yeah, sure.
yeah, so my question is that eventually, since we are computing covariance only, so I can also use NumPy's covariance functionality for the same, right?
Oh, NumPy had a covariance function. Okay,
Yeah,
sure
that's
then. Yeah,
true. I
you
mean,
could
yeah.
use that as well. I was unaware of it.
Thank you.
Yeah, okay.
Yash.
Oh, I had asked my question. I forgot to put down my
Okay,
hand.
okay, all right. So I think we are done with questions.
Oh, right. NumPy has a covariance function. Yeah, then in that case, you can use this function as well to compute your covariance from the data. Yes. Yeah. But yeah, so I guess this will be much easier. So just call np.co and then get your covariance matrix. So it takes as input 1D or 2D array containing multiple variables and observations. Each row represents a variable, and each row represents a variable, and each column a single observation of all those variables. So I think you will have to take, when you call this, you will have to take a transpose first and then call
Yes,
it because of
exactly.
the,
Yeah, yeah. Yeah,
yeah.
we have to take
Okay,
the class.
right. Okay, thank you for the information. Yeah. All right. So then it's much easier to find a covariance, and then you will have estimate of pi, mu, and sigma. Okay. Okay. Now that you have all the parameters, you can visualize the likelihood. So by likelihood, I mean p of x given c1 and p of x given c2, and so basically these normal distributions. So you can use all of these functions: np.mgrid, multivariate normal pdf, plot surface, and contour f. Now to help you, if you go to the notebook that we used for the lecture, uh, we already had generated uh, surface plot and contour plot, and you can just use the same code to generate your plot. So essentially what you have to change is, here we are passing the mean and the covariance. So instead of using this mean and covariance, you'll have to use the mean and covariance that you computed in the previous section. So that is mu1 and sigma1 and mu2 and sigma2. So out here, I'm just plotting one Gaussian. What you have to do is you will have to run this thing twice. So essentially you'll have to say you generate RV1 and RV2, and then you pass in the mean one. So this would be some mean, sorry, you pass in some different values of mean and covariance, and then inside the plot surface you'll have to call this line twice. So one for RV1 and one for RV2, and then I have suggested that for yeah, so for class 1 you use red color, and for class 2 you use blue color so that you can see the data clearly, and also use alpha equal to point 0.5. So what this alpha will help you do is it will help you blend in the two plots together in the same figure. So you simply call alpha is equal to 0.5, equal to 0.5, and then you just, and you do this also for your contour plot. So maybe let's just look at an example.
Essentially, alpha is transparency.
Right, yeah, exactly, yeah. Yeah, right. So you can just see the two figures together in the same plot if you use this transparency. Okay, so that was about visualizing the likelihood. And once you have the likelihood, you can also compute the posterior. So the way you compute the posterior is you have to compute the posterior separately for each data point. So what I mean to say is when you get this x comma y from the mesh grid, so these x will give you the x coordinates of all the points and y will give you the y coordinates of all the points. So for each x and y separately, you'd have to compute the posterior. So when you have uh, so when you pass in your this yeah this when you pass in rv1.pdf and here you pass in this pause, so pause contains all the x and y coordinates, you essentially get the likelihood at all the points. So similarly similarly, since you already have the prior, so for each data point you can compute the posterior using you for each so for each of the points in pose you will have to multiply the prior and the likelihood and then divided by the prior and likelihood plus prior and likelihood for the two classes separately. So do you have any questions for computing the posterior?
Let's pause for some questions. Any questions?
Yeah.
So the output of the when we will plot the posteriors, both of them. So the output comes out something like two curves which are rising and which are kind of intersecting with each other. Something like that will be the output, right? I mean,
Yeah. So one of them will go down
Can
at
you
the
repeat your
decision
question?
boundary,
We
the
missed.
other one will
I think
start
the audio
rising.
wasn't very good.
and my question is, I mean, like the contour plots and the surface plots, how will they look like? Will they look like they are
Ankur, did
kind
you
of,
get his question?
Yeah, I got his question.
because for me it looks like something which like two curves are kind of cutting through each other and there's a boundary line which can be between them, right? So I think, is that correct or
Yeah, I think you should be correct. So yeah, so it should come like the when you look at the contour plot, it should look like a curve like this. Is it?
yeah, yeah,
Okay.
okay, yes, thank you.
Yeah. Okay.
There's a question by Aryan. Transpose to be taken along which matrix in case of 3D arrays? I mean, which order? So transpose can be
Okay.
taken in different orders in ND arrays. So can you
Right.
explain
Right.
where was that
Uh,
taken? Yeah.
Yeah, so I was explaining it to help you compute the covariance matrix. So essentially, I was saying that if you have data in this shape, 10 cross 2, you can first reshape the 2D array into 3D array and then compute the multiplication. So, but I guess it's much easier to use the covariance function, which is already given here. So then I guess just use this; that will be much easier to use. Okay, great. So should I go ahead?
Yes.
Okay. So now once you have the posterior, so finding the decision boundary is pretty straightforward. So you will have a matrix that will contain your posterior for class one, and you will have a matrix that will contain the posterior for class two. You just check. You just do something like uh, you do something like this. So let's say you have your posterior stored in this variable and posterior one stored in this variable. So if you just if you just use this statement, you will get an output matrix which will contain true and false, And so true will mean that posterior of 2 is greater than 1 at that point, and 1 will mean posterior of 1 is greater at that point. And then you can call the same plot functions, that is surface plot and contour plot, to plot this variable. So yeah, so that will give you the decision boundary. And on the same plot, you can scatter your data points from class 1 and class 2. That will help you visualize that your decision boundary is doing a good job of finding the boundary between where are your points from class 1 and where are your points from class 2.
We have to
And
just plot that. You can continue. Sorry.
no, you can ask your question.
No, no. I'm just asking. Like, I just want to confirm that we just have to plot the boolean output, right? That's the only thing we have to plot.
Right, exactly. Right,
Okay.
exactly.
Yeah,
Yeah.
thank you.
Okay. And finally, we have given you some test data on which you can test your model. So test data is stored in a slightly different format. So it's a data containing three columns. So first feature, second feature, and the class. So then we have and then we have already separated it out for you. So now finally, test data will contain your two features, x1 and x2, but it's not separated out between whether it's from class 1 or class 2. They are all stored together because it's your test data. You don't a priori know what is the true class. But to check the performance, we have also given the label. So for each row, whether the row is coming from class 1 or class 2 is given in test label. So now you can so over here you have computed the posterior for over the values in the pool or values from the mesh grid, but you have to simply find out the same posterior for the points in the test data. So once you find the so how do you find the posterior? You just do the same kind of computation. First you find out the likelihood, and then you like use the prior to compute the posterior. So once you have the posterior, you can use a similar decision rule, greater in this, yeah, okay, so you can use a greater, whichever one is greater, you can assign it, and then you can compare whether it's correct or not by using the classification report function that you are already aware of. Yeah, so one thing to note is in your test label, the 0 would mean it's from class 1 and 1 would mean it's from class 2. So essentially, if you use something like mm, maybe you would have to reverse this sign. Oh no, I guess this is fine. Yeah, you can use this decision rule to compute the output over here as well, and then call the classification report function. So does anyone have any question?
I don't see any questions. Anyone has questions?
Mm, I had a question
Yeah, go
regarding
ahead.
posterior probabilities. How do I
Okay.
store the posterior probability for each point? Do I make a function? That's what I did actually.
Yeah, so you could use a function, but you can also do it all together. So you have your prior one, and you have your and if you already also have your, so you have your prior and you have your likelihood, right? So these are already stored in arrays, right?
Are they? The multivariate normal is stored in the RV1 object, right?
Oh, right, it's stored in the rv1 object, but you can save the output to a variable. So I'll show you. So if you have rv1.pdf, so if you do something like like this, it will store the output to a array. So you get all the outputs in the form of an array. So then you can just do multiply your prior and your likelihood and then divide by basically this sum. Does it make it clear? Does it clarify?
But then the pos has some particular range, right? What if the decision boundary lies outside that range?
Oh, that is true. So yeah, so we made sure that the decision boundary lies within that range in your example.
Oh, okay. Thank you.
Yeah. Yep. You're welcome.
There's a question from YouTube by Shekhar. He's saying that that trick that you used, what was that trick? The
Yeah.
matrix multiplication trick is not in the notebook. Can you update it, please?
Okay, sure. Yeah, we'll definitely update it. Maybe we can put it in a tutorial notebook. Uh, and actually for this problem, maybe you will not need this because you have the NumPy covariance matrix. But yeah, later on you might need this trick somewhere if you are solving some other problem. So we will update it.
Thanks. I don't see any more questions.
Okay, I guess
Ashish is
then
asking, can we ask questions from the lecture? Are we done with the assignment?
I think so.
Okay. Ashish, what's your question?
So my question is, can you just talk a little bit about the decision boundary part? I mean, here it is clear, but I did miss it. And Amit sir yesterday told like it's like mu1 minus mu2. I could not understand it. So can you like if repeat that thing would be great.
No, I didn't say it is mu1 minus mu2.
I mean,
It's
I think I heard it wrong or something.
it's a G1 minus G2 equal to 0, which means G1 equal to G2.
Yeah.
So graphically, how would it be? Because here it's basically if you see in this case it's mu like W is mu1 minus mu2. But if you go down and you scroll, there's an arbitrary case, right? Like I think
Yes.
arbitrary case.
Yeah, this one.
Yeah, in this case there is sigma inverse, right? Like when we are
Yes. So,
calculating.
so this will give you a quadratic boundary, whereas
Yeah.
whenever sigma inverse cancels out, then it gives you a linear boundary. So sigma inverse cancels out if sigma 1 is equal to sigma 2.
Okay, yeah, okay. Now I get it. Thank you.
Okay.
Okay.
Other questions from the lecture? All right.
So
Anything else anyone wants to discuss? Yeah, Ankur, you had something to say?
yeah, I mean, I meant to say that if everything is done, then next Sudhakar can take up the quiz questions.
Okay, let's do that.
Yeah, sure. Thank you, Ankur. I will discuss the pre-quiz questions now.
1 second. Kasina has a question.
So, sure, sure.
Yeah, Ankur, I wanted to know, could you please could you please explain a bit about the concept of covariance?
About the concept of covariance. Okay, sure.
Yeah,
So, okay. Okay, so if we just look at a 1D Gaussian case, so in that case your covariance is simply a scalar which is the square of the sigma. So what it says is how much is your data spread out. So if
you're
you
not
increase
audible.
I'm not audible. Am I audible now? Okay. So what your covariance says is that how much is your data spread out. So if your sigma is larger, your data will be spread out more. So in this case, first I have a sigma of zero point 0.5. So covariance is square of zero point 0.5, which is 0.25. Now if I increase my covariance to 2, so, sorry, sigma to 2, then if you see that the Gaussian is spread out. Now the same concept extends when we go to multi-dimensions. So if you have a multi-dimensional array, yeah, so if you have a multi-dimensional array which is a diagonal matrix, so in this case in which the covariance is diagonal. So if you have diagonal, essentially the diagonal elements say what is the 1D equivalent covariance term for each of these variables. So if you simply you can think all of think this to be the first diagonal element to be the covariance for the first dimension of your feature, and the second diagonal element to be the covariance of your second dimension of your feature. And if you and also if it's diagonal, what it means is that your features are independent of each other. So this multivariate normal is can be expressed as product of first product of two multivariate normals. So basically you can split this out, you can split out this in equations into two variables. This will be a 1D normal and another 1D normal and the product of the two. And so since these diagonal elements say again how much is the covariance in 1D case, again the same concept extends. So if you increase these covariance terms, you will see that the Gaussians start to spread out, right? So if when I am putting 3, it is more spread out, but if I put in a smaller number, then it will not be spread out. It will be the data will be concentrated. And and now let's look at the off diagonal elements. So if these are not zero, what it means is how much is the so when you compute, if you remember how do you actually compute the variance of a single scalar? You do x minus mu, and then you multiply it with you do x minus mu squared, and then you take the average, right? So but since now you have multidimensionals, instead you can do it across two different variables. So there is x1 minus mu1. This is your where x1 means the first dimension of your feature, and x2 minus mu2, and you take average across this. So over here it was x minus mu multiplied by x minus mu. Now you have x1 minus mu1 multiplied by x2 minus mu2, and then you take average over this. So that will essentially give you this element. So, and if this element is zero, it means that the dimensions are independent. And if it's not zero, then you get some dimensions. And this independent and non-independent cases can also be seen from the plots. So let's say I put in some non-zero values over here. I should turn on the contour plot. Okay. IP is not defined. Okay, so now since there are non-diagonal elements, we see that the Gaussian is not axis aligned. So an axis aligned Gaussian is what is an independent Gaussian, because then the features do not depend on each other. Yeah, so if there are no off diagonal elements, then you get independent Gaussians. Yeah. Uh, does it clarify your question?
Uh, yeah, sure.
Okay. So someone asked, can you suggest other reading material for Bayesian theory? Uh, Yeah, sure. I'll collect some material and post it. And I forgot what is np.mgrid is. Can someone explain? So np.mgrid will generate xy coordinates along a range. So if you want to so in this case we want to have x and y coordinates in -5 to +5 range. So if you give -5 to +5 and 0.01, this will give you points spaced with 0.01 from -5 to +5, and this will it will do it for the first dimension, and we are doing the same thing for the second dimension as well. So now our x will contain the x coordinates and y will contain the y coordinates. Yeah, and each of them will be will be like arrays. Yeah, two-dimensional arrays.
Hello. May I ask a doubt?
Yeah, sure, go ahead.
Yeah. So this is regarding the assignment. I was trying to plot the decision boundary.
Okay,
So yeah, now that I have stored it in a variable, the posterior probabilities,
right,
how do I put in a line? Because the exact values where PC2 and PC1 are equal might not be among in that range, as in the values are moving up some step, right? So
right, right.
the step is 0.001, but the value at which they turn out to be equal is most probably going to be more, going to have more significant digits to the right. So
That
will
is
it be
true.
able to plot? How do I plot it?
So yeah, you are right. So we are just trying to find the approximate boundary. So if you do something
Oh,
like
put
this,
in an epsilon, right?
um, epsilon. Uh, are you? Is your question like more related to how do you implement it in the code, or it's a more theoretic question you want to understand how
No, no, in
it's
the code, because understanding
in
it
the
is
code, right?
yeah, yeah. Understanding it is
Okay,
pretty
so
straightforward. Looks clean.
okay, okay, great. So in the code, it's very simple. So if you have your posterior stored in two values, posterior two and posterior one, you can
Yes.
just use decision equal to posterior two
Oh,
greater than posterior one, and then you put plot find a contour plot of decision. So if you so decision will what will decision contain? It will wherever the in the region posterior two is greater, it will contain true, and in the other regions it will contain false. So
yes.
if you just do a contour plot of this decision, you will get two values. For true, you will get one color, and for false, you will get another color. So you can directly visualize the boundary.
Yes, yes. Thank you.
Yeah, you're welcome. I guess then Sudhakar can you can move ahead with the quiz questions.
I okay, yeah, sure. I will discuss the
Okay.
quiz questions now.
Okay.
Yeah,
Great.
so I will share my screen. Yeah, so okay, so yeah, the first question was, am I audible to everyone? Am I audible to everyone?
Yes.
Yeah, sure. So the first question was like this HIV thing. So if someone tests positive, then what is the probability that they actually are HIV positive? So I think all of the questions which were given in this quiz was based on Bayes theorem. So in this question, it means we can simply apply that the positive thing, like uh, they are actual positive given that someone tests positive. So that should be equal to applying the Bayes rule. That should be equal to 99% into 0.3% divided by 99% into 0.3% plus 1% into 99.7%, means of course percent means you have to divide by 100. So yeah, so then you will, I think you might be getting this answer was the right answer, I think. Yeah, I think someone has questions, so Myth.
Yeah, hi. So I have this question. When you say that some test has an accuracy of 99%, that means and in this it is in both directions. So the result are true for
Yes.
99% of the cases, right? So if
Yeah,
someone
means
has
in both
test,
the directions, means if
yeah,
it is
so
saying,
yeah, so
yeah, means
suppose,
if it is saying that someone is not HIV positive, means again the same 99%
yeah,
accuracy is there.
exactly, exactly. So in this case, if the result has come positive in the test, that means 99% chance he's actually positive because the test has that accuracy, right? So
Okay, go
in
ahead.
this question, Bayes rule will not apply because the question is very straightforward that if the test uh, confirms positive, if the test has come out positive, then according to the accuracy of the test, 99% of time he will be positive, and that is intuitive also, right? Because the
No, no,
test
no,
is
no,
so
no, no, no,
accurate.
no, 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 no.
You so you please explain the last line. If someone tests positive, means someone has
Means,
undergone this test and the result has come positive.
mhm,
How
yeah,
probable he is that he is actually having HIV positive? This is the
yes,
question, right?
yes. So, yes, exactly. So one thing is given, and you have to find the probability that A given B. Okay, so there are two different events, and you have to find the probability of one event given that another event has already occurred. So here we have to apply conditional probability,
Yes, but the
and that's why means 99%. Yeah, yeah, please tell.
yeah. So 99% accuracy means what? Oh, if the result has come
Means the
positive,
test gave, yeah, the chances are that 99% chances are that the test is giving the correct result. Means that person was positive and it gave positive, was negative, gave negative, in both the directions. Means if it is saying yes, 99% chance is that that person has HIV. If it is saying no, 99% chance is that that person has not HIV.
yeah. So this is the accuracy of the test, that whatever the result comes, 99% of the time the result is true, right?
Yes,
So,
means
so now the
for,
result has come something.
mhm.
What is, yeah,
Sudhakar, do you mind if I maybe I can clarify it?
Sure, sure, Ankur, yeah, go ahead.
Okay, so if you think of it in terms of probability, maybe it will be more clear. So what 99% says, it's the probability of being correct given you are HIV positive, or probability of correct given you are not HIV positive, right? But what the question asks you is, what is the the probability of HIV given the test says it's positive? Do you understand the difference? So there is a
okay,
slight difference
yes,
over here.
I, I, I got it. The first
Yeah,
statement is also a conditional statement. Given you
right.
are this 99% of the time. Okay, I got it.
Yeah. Okay, cool.
Thank you.
Yeah.
Yeah, so I think yeah, Ankur cleared it. So yeah, I think this is pretty much clear now. And then the next question. So again, it is a conditional probability. So like, okay, so the probability that the family also own a dog, given that they have a cat. So simple, we can miss like probability of A given B. So probability of A intersection B upon probability of B. So it's like we can multiply these two, 36% and this 22%, and then we can divide by this 30%. So it will be like dog and cat, we are multiplying these two, 36 and 22, and then dividing it by 30%. So in that case you will be getting the right answer. And then it was simple two dice rolling question. So the sum has to be 8. There is no condition involved here. So I think five instances are there. Five instances are there, like means you can like 2 6 3 5 5 3 4 4 6 2 likewise. So those five are our means desired outcomes, and 36 is the total sample space. So this would be the right answer, 5 upon 36. Now if we add a condition in this question, then the answer will change definitely, because now we have to find the sum is 8 given the first die shows a 3. So in that case first die shows a 3 and the sum has to be 8. So in that case the only means true case, like the numerator thing will be 3 5. So 1 upon 36, and the first die shows a 3, that will be 6, total 6 cases. So 1 upon 36 by 6 upon 36, so that should result into 1 upon 6. So I think that should be the right answer. And then these two questions were like selecting a ball from Miss bag having different colors of different balls of different color. So in this question we were having 5 blue and 8 red balls, and then it was like we are each ball we are selecting one ball and it is returned again with an additional ball of the same color. So we are drawing 3 balls in this way, and 3 balls have to be blue. So initially when we are drawing, and if we assume that the first ball has to be blue, so the chance is 5 upon 13, 5 blue upon 5 plus 8. Now after withdrawing one ball, we will be putting again one blue ball, so the number of blue balls will be 6 now. So similar case, we will having 5 by 13, again one increment, 6 upon 14, again 7 upon 15, because we are putting the ball again in the bag with one extra ball of the same color. So I think this should be the right answer. And then in this case, the point, the means the same thing is happening, except that we are trying to find the probability that only one ball is blue. So in this case, I think this should be the answer, like yeah. So 5 by 13 means only one ball is blue. So we are assuming that for the five blue balls, so 5 by 13, now the remaining two balls should not be blue. So remaining two, they have to be red. So that's why the number of 8 red balls. So now we are having like 5 balls into 8 upon 14 to 9 by 15, and then 3 balls have to be drawn. So there will be 3 orders of that thing. So that's why 3 into 5 upon 13. So I think this one was the right answer. So yeah, so these were the quiz questions. uh, Anyone having any doubt, so we can talk about. Yeah, and one more thing, that we have started uploading the solutions of the assignments. As of now, the two assignments of data science, their solutions have been uploaded, and it's like that the solution which have been given, it's not the ultimate one. It's that what we have found that this should be a better way to do it. Of course, you guys can find another better way, another optimized way to solve the same problem. So you can do it on your own. You can keep experimenting, and we will upload the remaining solutions shortly. In a couple of days, we will do all the solutions and upload it. Yeah, any questions? Uh, okay, in chat, are we having any questions?
There's a question by Arun. Is that known as the sensitivity of the test?
Is that known? Is sir? Is that known? So, what are we talking about?
Not sure. Sensitivity of a test.
Okay. I am also not sure about sense. I think sensitivity, specificity, it was in terms of precision and recall. So if it has to do something with that, then
So sensitivity means that what percent of truly positive you really catch positive, and specificity
yes.
means that you don't include random non-positive stuff into the positive stuff. Okay, so there is sensitivity and specificity. There's a trade-off between the two. If you increase sensitivity, you lose specificity, and vice versa, by changing the decision threshold, by moving the decision boundary closer to one class, or class positive class, or the negative class. Okay. Is that clear? And there is another thing which is called, in hypothesis testing, we had that confidence interval. So that was, or a p-value, that basically told you what is the chance. So if p-value is 0.01, then there is 1% chance that the observation was due to null hypothesis and not the alternate hypothesis. So there is 99% confidence that with which we can accept the alternate hypothesis in that case. Hritik, what's your question? Hritik Jaiswal, you have a question? So can you give more example related to Bayes? Uh, Ankur and Sudhakar, you want to take that?
I think we have added one pre-work on the means examples of Bayes theorem, the second pre-work, I think, that we have uploaded on our website. Maybe you could have a look, or else if we find some more problems, we will definitely post in the campus wire. That we can also do.
Okay. So are we done with the quiz?
Yes, sir. Quiz is done. Yes, sir.
Any other questions? All right, then I guess we can call it a day.
All right. Okay. Thanks everyone. Thanks Ankur and Sudhakar.
Yeah, thank you everyone.
Thank you.